Hi there, Chemistry 11 and Science 10 students. So a few things to cover today. First of all, I just wanted to mention to the Science 10 students among you, waiting for a few people on the safety plans for your projects, for your chemistry projects. To just recall, that's to do a chemical reaction at home, simple, hands-on chemical reaction that often you're going to be even doing in a home setting, either one that is actually directly useful to you or one that's kind of an example of a broader concept. The list is given in the handout. Again, I'm looking for you to choose one of those reactions, maybe come up with one of your own. Let me know exactly what you want to do so I can vet it to make sure it's a safe reaction. Anything can be done not safely, although all the reactions I have chosen for that list can be done perfectly safely without any problems at home in a home environment. I have no hesitation, but I want to know that you've got a plan for that safety piece. If you're in Chemistry 11 and have some interest in doing this kind of a project for some extra credit marks, I can do that. Path B students in Chemistry 11, I'd like to talk about that project with you as well. That would be something I'd have you do. Haven't got any of you guys yet on who are in Path B, but if that's somewhere you want to go, then we can do that. And again, if you're in a Path A situation for Chem 11, then I'll post that for you guys and you can try it out for some extra marks. So looking so far, you in Science 10 and Chemistry 11, you're basically doing the same thing kind of coincidentally right now. You've been looking at conservation laws. So Chemistry 11 yesterday, I introduced you to more conservation laws than you had seen in Science 10. I told you that in any chemical or physical change that although there might be a change in the substances that are present, the amount of matter, the mass, which you would measure as weight, does not change. This is a fundamental property of the universe. It's a physical law. I told you that underlying that is the fact that the atoms themselves remain. They're not destroyed in a reaction. New atoms are not created in a chemical reaction. They change arrangements, and this is what it means to get a different chemical compound in a reaction. Atoms or either alone or part of a molecule are rearranged in a chemical reaction to create a different arrangement, which is a different chemical with different chemical properties. So we have the law of conservation of mass, Science 10, that's you as well. Law of conservation of atoms, which really applies to you both. The atoms are not created or destroyed, and this is why mass doesn't change. And this is extremely important for what we're looking at for today's lesson that really applies to both of you. So I'm just going to also put some notes up that really are things that you've looked at before, but again, should as well put you in the headspace for completing that conservation of mass lab. Science 10, most of you have done that already. Chemistry 11, I assigned it to you a bit more recently, although I showed you and a kind of example of that lab yesterday in yesterday's video. Chose a different reaction, showed similar results, although again I demonstrated that it's hard to perfectly show the law of conservation of the mass unless you have better equipment than I do. Although I did show you how with a closed system you can have a negligibly detectable change in mass when you have a reaction happening in a closed system, acknowledging there's always sources for experimental error. But when you open the system and you've got some kind of phase change, like a gas being released, it can seem as if mass is being destroyed, but no, we can see a gas is being released. That accounts for some of the mass in the chemical reaction that's leaving the system. And so the matter is not being destroyed, but its weight is changing. The weight of the substance that remains, I should say, is changing, which accounts for what might seem to be a decrease in mass. In a closed system, mass will not change. In an open system, you can detect a mass change of the substance that remain present. A detection is a change in weight, even though the actual number of atoms and the mass itself does not change in a chemical or physical change or reaction. So I hope that that makes clear where I've kind of been splitting up this concept of an open and a closed system. So for any chemical or physical change in a closed system, like I showed you with reaction 1 for the lab, like a sealed flask. Here we have a reaction happening inside a sealed flask. It's stoppered off, and the mass is not going to change if that's sealed properly. The mass will not change, and if you have good enough equipment, you won't detect a weight change either. The mass does not change, and the number of atoms and also the type of atoms does not change. It's not just a matter of a count of atoms. The chemical elements themselves do not change. You'd never have a chemical reaction that starts with, say, iron and oxygen and ends up with sodium and chlorine. The mass doesn't change, the atoms are also conserved, and the identity of the chemical elements similarly doesn't change. This becomes very important for looking at the skill you're going to look at today. Chemistry 11, you've seen this before, but in my experience, it's the trickiest stuff in Science 10, and you also really need to know it for going forward in chemistry, especially, again, getting to the heart of Chemistry 11, which is Unit 7. Science 10, this is the first time you've seen this, and I'd like you to get a lot of practice at it. Again, I just said it's probably the hardest concept in Science 10, so you're going to have to work at this a little bit more. I give an example of a chemical reaction, which I wish I could demonstrate, but I can't. It's a formation reaction, a reaction where you're taking two elements, combining them and making one compound. The elements in question, sodium and chlorine. Now, you may be aware, Science 9, from Science 9, that chlorine gas, the atoms in chlorine gas, don't like to be alone. In pure chlorine gas, what happens is the individual atoms of chlorine join together and form single bonds between the chlorine atoms. This is chlorine gas, pairs of chlorine atoms. We say Cl2 to communicate the fact that it's as an element, as a pure element, the atoms are present in pairs. Just like oxygen, O2, hydrogen, H2, fluorine, F2, and so on. There's a lot of these diatomic elements. Here's an example then of a chemical reaction. Sodium and chlorine. Here we go. I've underlined them here. React to form sodium chloride. We're making table salt here. The reactants are sodium and chlorine, and the product is sodium chloride. Now, you have all seen element symbols in the periodic table. Most of you know that sodium is Na. You probably know that chlorine is Cl. We can show that using fewer characters, using the element symbols. Na is your sodium. But you don't put down Cl. You put down Cl2 because chlorine is diatomic. So Na is your sodium. Plus corresponds to the word and. Cl2 is your chlorine gas. The arrow, and I'm looking in black right now, means makes. NaCl, sodium chloride. Now, what I've just shown you is called a skeleton equation. Science 10, if you're filling in your notes, that's great. There's an example skeleton equation for you. Now, I want to show you something about that, though, and that is, well, first of all, a kind of visual diagram. Science 10, I've shown this to you. Chem 11, and won't hurt to look at it. Let's represent a sodium atom as a ball. Atoms are a bit like that. And a chlorine molecule as a pair of chlorine atoms joined together. That's two chlorine atoms joined together. This is, again, chlorine gas. Reacts to form, there's your blue arrow, NaCl. I'll just also have you notice, just for, to be correct about it, it's an ionic compound, and so it's made out of Na plus ions and Cl minus ions. Chloride is your Cl minus. What I consider that to be there is kind of a visual diagram. You won't normally see those put into textbooks, but I kind of like them. It shows you visually what's happening. An atom of sodium is bonding with an atom of chlorine to make sodium chloride. But there's a problem here. The problem is that, as I have written it, this violates the law of conservation of mass. It violates the law of conservation of atoms. Let's look at why. These here, right there in the middle of the screen, are your reactants. Count the atoms. We have 1 sodium atom and 2 chlorine atoms. Let's count these atoms. Uh-oh, we've got 1 of each. What we would say about this is that it's not chemically balanced. It appears like out of my back pocket, I've pulled out some extra chlorine from one side. That's not allowed. This doesn't happen in nature. Extra chlorine atoms don't, they don't just vanish in a chemical reaction. What we need to do is we need to balance this. First of all, I'm going to show you the visual balancing of that reaction. So again, I'm written down here. The problem, you want to put this in your notes, go ahead. Problem. The skeleton equation and diagram above seem to violate the conservation laws. The solution, you add sodium to the reactants and you add sodium chloride to the products. Watch what happens. Instead of just 1 sodium atom, I'm putting in 2 here. The Cl2, I'm not changing. And instead of just 1 sodium chloride, what's called a formula unit, I'm putting in 2 of them. Now watch what I do below that I put inside the rectangle, okay? That whole thing I put into the rectangle. Notice this. 2 sodiums, right? I'm going to try and do this here. Right there. That's your 2. That's called a coefficient. That tells you you've got 2 sodium atoms. I don't put 1 for chlorine. It's got a subscript that tells us that this is 2 chlorine atoms in a molecule, but I'm not adding more chlorine to my reaction. That stays the same. And similarly, 1, 2, 4 millunits of sodium chloride, and I communicate that with this 2 right here. That's your coefficient. What I've just done, red writing here, is I've created a balanced chemical equation. Science 10, you might want to add that to your notes. You're going to see a lot of those, and I hope you're going to get used to doing them yourself. So the next question comes up, well, how do you do this? I've created a worksheet, Chemistry 11, for you folks. I've already got some people who've submitted me their worksheets. Great. Some of you maybe could use a bit of review on this. Science 10, this is the first time you've seen this. What I've done on this board over here is I've written up some examples from the worksheet. There will always be different video resources you'll find on YouTube or other sources telling you how to balance chemical equations. I'm not the only person who can do this for you. I will show you how I do it. The first question here is, I'm going to, there. You can pause the video right there if you want to, and I'm going to put the computer down here. The reaction for question 1 is this. Sodium and iodine react to produce sodium iodide. Okay. Notice what I did in the red writing. Let's go back to that again just to be clear. In the red writing right underneath that reaction, I put a little 1 inside a circle. That just means that step 1. Notice what I also did over right here, middle of the screen. I put a little ×2. That is my saying, that's my next action. That's what I'm going to do next. I'm going to multiply this whole thing by 2. What I'm saying here is I'm going to add a coefficient. That coefficient goes before the chemical formula. Coefficients always go before the chemical formula. You don't put them somewhere within the chemical formula. That would change the chemical that's there. That's not allowed. They always go before the chemical formula. So here I've done it in red. Step 2. All right, looking at the middle of the stream, we're going to scan across. Na plus I2 makes 2 NaI. Again, iodine is also diatomic. Iodine atoms get lonely. They bond in pairs. Here's what's happened now. What I've got written in red, and I should have mentioned this before, under the reaction is kind of a tally. It's a count. I've counted the number of atoms that are present in the equation as it is written above. So I counted here for step 1. Now I've got 1 sodium atom. I've got 2 iodine atoms, I2. And on this side I have 1 of each. No subscripts tells us 1. Here, after I've done that one step, I multiplied this whole thing by 2. I now have 2 sodiums and 2 iodines. Yeah, let me be clear on that too. That coefficient applies to the whole formula. So if I put 2 NaI, that doesn't just mean I'm like, oh, there's 2 sodiums and doesn't apply to the iodide. It does. It applies to the entire formula. So the 2 NaI, if you change that, you put that subscript there, that means you have to change everything that comes in that chemical formula. This is why, for step 2, we now have 2 sodiums and 2 iodides. That's step 2 only. We're not done. How do we know we're not done? We know we're not done because of my tally. Look, for my tally for step 2, I've got 1 sodium atom on this side and 2 on this side. Until all these numbers here and here line up perfectly, are equal, I won't be done. Here is my next action. I'm going to take this sodium here, I'm going to times it by 2. In other words, I'm going to put in a coefficient of 2. And there it is right there. This is step 3. 2 sodiums plus iodine makes 2 NaI. I kept that coefficient. Now we do a tally. 2 sodiums, 2 iodines. 2 sodiums and 2 iodines. I put a giant tick in there to show, yeah, it's correct. What's the word? I found it's correct. I can't remember the word for it. This is demonstrating that it's correct because all the numbers after the values for those elements are equal across the board. Verify, that's it. I verified the answer. All right, I want to do question 3. Question 3 involves polyatomic ions. I'll say one thing. I'm not actually done the question. I kind of ran out of space, but I'll finish it for you. So here's the question. We have potassium phosphate plus HCl, hydrochloric acid, reacts to make potassium chloride and phosphoric acid. Just your reaction. We start. Step 1, we tally everything. And here I'm going to save you piles of time. Watch this. Notice this. The PO4, that phosphate ion, you learned about polyatomic ions in Science 9, it stays the same on both sides. Look, phosphate here, phosphate here. This is extremely useful because it means you don't have to tally for P and tally for O. Here, you can just say units of phosphate. This will save you time, believe me. And what is our tally? At the start, we have 3 on the reactant side. We got 3 potassium, 1 phosphate, 1 hydrogen, 1 chloride. On the product side, we have 1, 1, 3, and 1. So it's not balanced. By the way, sometimes they are balanced. They start out balanced. Step 2. What I did is I took this here, the K, and I times it by 3. That accounts for this coefficient right here, that 3. Now let's look what happened. Okay. That's a step 2. We have 3 potassium still, 1 phosphate, 1 H. You can see these are the values right here for the reactants and here for the products. And unfortunately, we're not yet balanced, but we're close. Notice I put an action right here. This will be my next action, to times this by 3. I'm going to do that in this same space. I'm going to put the computer down. So we're going to make this step 3. You saw step 2 written up there already. For step 3, I'm going to take that H and multiply it by 3. But let me be clear. When I do that, I'm also multiplying the Cl by 3. Now let's do a retally of this side, because we didn't do anything to this side. 3K, 1PO4, 3H, and 3Cl. Look, because this 3 here, this coefficient right here, multiplies the chloride by 3 as well. 3133, 3133. It is balanced. So the coefficients for this are, well, there isn't one, so we say 1, not 0, it's 1, 1, 3, 3, and 1. This is now a balanced chemical equation. I just gave you your step 3. Big tick shows we're done. The next one I want to do is question 6. I'm going to do question 6 because many of you, even in chemistry 11, are going to find this tricky. If you're in science 10 and you can do these questions, I think you can, well, I believe these are the hardest questions in the course because they're kind of mathy. Question 6 involves a compound called ethane. You're burning the ethane. When I lived in the north once, and there was we lived in an oil town, and there was a huge stack at the end of the town. It was a flare stack, and out of the flare stack, there was a flame, always, like 24 hours a day, 365 days of the year, a 10-foot flare burning off. And when I got there, I was thinking, why are they continuously burning this compound, whatever it is, natural gas or something coming out of there, when they're just putting CO2 into the atmosphere? It seemed like such a waste. But then I asked the people at ESSO, and what they told me was that it's ethane, and they had no way of processing the ethane, and so they just burned it off. And in footage from the oil fields if you see a smokestack in an oil field situation with flame coming out of it, you can see it for miles, kilometers, that's probably ethane that they're burning that they can't otherwise use. Ethane is a molecule with 2 carbon atoms and 6 hydrogen atoms around it. So we say its formula is C2H6. It burns. It burns in the presence of oxygen to make carbon dioxide and water. This is called a combustion reaction. Chem 11, you know this. Science 10, you'll learn it. Here's the reaction. C2H6 plus O2, here I'll go like that. C2H6 plus O2 makes CO2 and H2O, water. I begin step 1 with a tally of what's there. We have 3 elements, carbon, hydrogen, and oxygen. For the reactant side, we have 2, 6, and 2 as our numbers. How do I know the 2? C2, it's got 2 carbons. How many hydrogens? Well, it's got 6. You can see it right there. How many oxygens? The 2 subscript right there tells us we got 2. And in here, well, this is a little harder. We have 1 carbon atom and 3 oxygen atoms and 2 hydrogen atoms. Doing them in the same order, I show it as 1, 2, and 3 here. 1, 2, and 3. My first action is going to be to times that C by 2 in the product. So here, let me show you what I did. Right there. The action's in the center of the screen. I'm doing that because I want to balance the carbon. No problem. All right, so when I do that, let's see what happens. This is step 2, right here in the middle of the screen. We now have C2H6 plus O2 makes 2 CO2 plus water. Now let's tally and see what we got. Are we balanced yet? The answer is, well, not yet. We didn't do anything to the reactant side, so it's still 2, 6, and 2. The C, H, and O for the product side, well, we now have 2 carbons. That's good. And now we have, count them out, 5 oxygens. 5 oxygens right there. We have 4 from the CO2 and 1 on the water. So that's 5. So we're not done, clearly. Our step 3, here's the action that is best to do. Let's try balancing the hydrogen. Here's how we're going to do it. We had 6 hydrogen on the product side. You see that right here. Let's balance hydrogen by switching things up on the reactant side. I'm going to times that by 3. This means I'm having to times the water by 3. Now look at the new equation. I'm putting it in the middle of the screen. C2H6 plus O2 reacts to make 2CO2 plus 3H2O. Again, remember that when I make a change for the on a formula with the coefficient, I'm changing everything inside that formula. So now we have 2, 6, and 2, and 2, 6, and 7. Oh, man. What a drag. So close, but so far. How are you going to balance that? Here's the trick. The trick is this. We go back to the reactant side. C2H6 and oxygen. It's in the middle of the screen now. I'm going to multiply that by 3.5, 3.5. This is a real smart trick I learned about recently. Multiplied by 3.5. Now you're not allowed in your final answer to have fractional numbers. It's got to be all whole numbers. That's fine. We'll get there. Look at this next step. We end up having C2H6 plus 3.5 oxygen reacts to make 2CO2 plus 3H2O. Okay, what's that looking like now? Well, reactant side, 2, 6, and 7. Product side, 2, 6, and 7. 2 carbons, 6 hydrogens, 7 oxygens. There's just one problem. It's that 3.5. How do you deal with the problem? The answer is right over here, and I'm labeling it as the hard step. Right there. The hard step is to get rid of that. Well, if you have any number that ends in 0.5, you multiply it by 2, you get a whole number. That's handy, but how do we work with that? How do you work that in here? The answer is you take the whole equation, and you multiply the whole equation by 2. And you got to be careful when you do this, because you're multiplying the whole thing by 2, not just one formula or another. The entire equation is multiplied by 2. And that'll get rid of your 3.5, and it'll turn it into a 7. Let's look at how that works out. We end up with 2 C2H6 plus 7 O2 reacts to make 4 CO2 plus 6 water. I multiplied every formula by 2 when I did this. Now, we verify. 2 times 2. Okay, 4 carbons. Why is that? All right, let's unpack that. We have 2 ethane molecules, each of which has 2 carbon molecules. 2 times 2 is 4. How about hydrogens? We have 2 of those molecules. Each of them has 6 atoms. 2 times 6 is 12. 7 times 2 for oxygen is 14. Over here, we've got 4 carbons. How about oxygens? Well, hey, we have to do a bit of thinking here. We've got 8 oxygens in the CO2s and 6 in the water. Well, 8 plus 6 is 14. And 6 times 2 is 12 as well. That's why I put a big tick in there, because it's now balanced. So the coefficient here, whenever you have, in fact, a hydrocarbon like this, with an even number of carbons, you got to do this little trick. If it's an odd number of carbons, like propane, you don't have to do that trick. That is now a balanced chemical equation. The next, and as you can see, step 5. That's why there are the hardest problems in Science 10. Here, this is working with a word equation. This is question 9. You don't get this information for question 9. Instead, for question 9, what you get is you're told it in words. And you kind of have to know the formulas. Science 10, I wouldn't be surprised if you didn't know these formulas, but that's okay. I'm telling you them now. Nitrogen is N2. Hydrogen is H2. What's ammonia? Well, ammonia is NH3. Oh, and by the way, remember that nitrogen and hydrogen are diatomic elements. We start out, we have 2 and 2 on the reactant side, and 1 and 3 on the product side. My action is I multiply this by 2. Now, when I do that, I am not just multiplying the nitrogen by 2, I'm multiplying the whole formula by 2. It all changes. So now we have 2 and 6 as the number of those atoms on the product side. We didn't do anything with the reactant side yet. My next action will be to multiply this one by 3. And now I end up with having multiplied the H2 by 3, N2 plus 3H2 makes 2 NH3. Verify. 2 nitrogens, 6 hydrogens on the product side. 2 nitrogens, 6 hydrogens on the reactant side. The tick means it's balanced. The coefficients are 1, 3, and 2. The next question, I thought I would show the answer in a bit of a different way. Because some of you might be like, all right, Mr. Koo, this is taking forever. Now, once you get more used to this, you will find you'll be able to do this with fewer steps. Here I give an example. We have question 15, zinc plus iron 3 chloride makes zinc chloride plus iron. That's what we're told in words. We need to unpack that and make that into a skeleton equation with the formulas, you know. Science 9, you'll hopefully remember that iron 3 chloride, well, iron is multivalent. The 3 means it's a plus 3 charge, so it's Fe3 plus, chlorides are minus 1, so the formula is FeCl3. So we have Zn plus FeCl3 makes ZnCl2 plus Fe. There's our skeleton equation. Is it balanced? That's the first question we ask. Well, we have an unbalanced equation, 1, 1, and 3. 1 Zn, 1 Fe, and 3 chlorides. And on the product side, we have 1, 1, and 2. My time saver is this. We're going to work with like a kind of lowest common multiple, like you do when you're making a chemical formula. We're going to multiply the Cl by 3 on one side, and we're going to multiply it by 2 on the other side. In other words, they're both going to be 6. 2 times 3 is 6. 3 times 2 is 6. That's going to be 2 steps in 1. The next here, I'm going to zoom in on this like there. Step 2 in the middle of the screen. I'm writing down what that gave me. And again, you can go back and pause that if you want to. Zn plus 2 FeCl3 makes 3 ZnCl2 plus Fe. Notice, I did that so I could balance the chlorines. Now we have 1 zinc, 2 irons, 6 chlorines, right? The 2 FeCl3 means 2 irons as well. And we have 3 ZnCl2, so now we got 3 zincs, 1 iron, and 6 chlorides. Chlorides are balanced. We're good for chlorides. Again, what I do here is I do 2 steps at once. We've got 1 zinc on one side, 3 zincs on another side, 2 irons on the reactant side, 1 on the product side. I'm just going to do 2 steps at the same time. Multiply the zinc by 3, multiply the iron on the product side by 2. Those actions are shown here and here. So what we end up with is 3 zinc plus 2 iron 3 chloride makes 3 ZnCl2, 3 zinc chlorides plus 2 irons. We verify. Well, that's 3 zinc, 2 irons, and 3 chlorides. I'm counting the atoms here because this is all about the conservation of atoms. 3 zinc, 2 iron, and 6 chlorides on the product side. It is now a balanced chemical equation, so that's the tick. You should always do a verification at the end. So, where are we at for time? Chem 11 students, I'm thinking you've probably got this. Science 10 students, you can stop the video now if you want. stop the video whenever. I'm going to do 2 more problems because I'm thinking that probably some of you would like a little bit more direction. And so I thought I would do questions 11 and 13. You can do whatever you want with this video, but I'm going to start them from the beginning. It's going to take a bit longer because I'm going to have to erase some stuff here. The ones I thought I would do are questions 11 and 13. Okay, question 11 is sodium sulfate plus calcium nitrate. All right, so sodium sulfate plus calcium nitrate reacts to produce sodium nitrate and calcium sulfate. Plus calcium sulfate. There's your word equation. This is a what's called a double replacement reaction that you guys in Science 10 are about to learn. You're in Chem 11, you're still watching this. Well, that was last year. What's being made here is what's called a precipitate. The 2 salts combine, the 2 ionic compounds combine, and one of the ionic compounds that it results from this has a very low solubility, and so it forms a solid ionic compound and drops to the bottom of the solution and is called a precipitate. So, let me get a better pencil. And first thing we need to do is we need to come up with the formulas for what's in there. Well, sodium sulfate is this. Na2SO4. Calcium nitrate is CaNO3 We're making sodium nitrate and calcium sulfate. You might not know that right off the bat because what I just told you relies on your knowing the charges on the polyatomic ions. Periodic table will tell you the charges on the metals. Na plus 1, Ca plus 2. The nitrate is a minus 1. The sulfate is a minus 2. So those are the formulas. You need to get to those formulas before you get to the balancing the equation. But we can work with this. I'm going to make life simpler and work all in blue. I'm going to count the particles. So, here's a case where you really don't want to break this down by the element. The nitrate stays as nitrate. The sulfate stays as sulfate. You're counting ions for this. It'll make your life a lot easier. Na2SO4, CaNO3. We have 2 sodiums. We know this because the subscript for the sodium is 2. We have 1 sulfate. We would know we had more than 1 sulfate if there was a bracket around the sulfate and a number underneath it. If there is not that bracket situation, we have 1 sulfate ion here. Calcium, we have 1 of them. Nitrate, we have these brackets with the 2 at the bottom. It tells us we've got two nitrate ions. Sodium, we've got 1 on this side, 1 nitrate, and 1 and 1. 1 of everything on the product side. So we first ask ourselves, is it balanced? And the answer is clearly, it's not balanced. So what can we do about it? Well, let's see. First action can be, how about we try and balance the sodiums? I'm going to do ×2 for this sodium right here. I'm going to write down the new resulting equation below that. So a line right here, Na2SO4 plus that makes 2 NaNO3 plus CaSO4. Okay. I put that 2 there, and I'd like you to remember that that 2 applies to the whole sodium nitrate, not just to the sodium part. So I did an action of times the sodium by 2, but I could have just easily put a ×2 next to the nitrate. In fact, you know what? I think I will. That might make a bit more sense to you. I put the ×2 next to both because, after all, we've got sodium nitrate, and that is working itself as a package, and so we're multiplying that by 2, and we're multiplying that by 2. It's not really doing the same. It's not really doing 2 things at once, because that one action makes both of those 2 things happen. Let's look at our product side and our reactant side and count our ions now. NaSO4, CaNO3, NaSO4, CaNO3. I know I'm not putting the ion charges on there. They're ions. Let's count these out. We didn't do anything to the product side, so we can just write in the 2, 1, 1, and 2. There's still 2 sodium atoms, 1 sulfate ion, 1 calcium ion, and 2 nitrates. On this side, 2, 1, 1, 2. That's nice. It's balanced. Let's be sure about this. 2 sodiums, 2 sodiums. 1 sulfate, yes. 1 calcium, yes. 2 nitrates, yes. 2 sodiums, 2 sodiums. 2 nitrates, 2 nitrates, and 1 of each of the calciums and sulfates. All we needed to do here, it was a one-step solution. We put a 2 on the sodium nitrate on the product side, and it's balanced. Here, you're getting a correct answer to that question relied more on having the basic skills of balancing chemical equations and on knowing how to state those formulas correctly. You know how to do those things, then that's a question you can succeed at. The last question I thought I would do, I'm just sticking to odd numbers, is question 13. Any more questions that you have that you're having trouble with, please just email or chat. So question 13. You know what? I'm not going to do question 13. I'm going to do a different one. I'm going to do question 10. Question 10 is a bit harder. So the question is, sodium oxide reacts with water to produce sodium hydroxide. It is only slightly harder because we have 2 oxygen atoms in play here. In fact, every entity has oxygen in it. It actually might not be hard at all. Let's have a look what happens. First of all, I know that sodium oxide is Na2O. I know that because each sodium ion it's got a +1 charge. Each oxide ion has got a -2 charge. So you need 2 sodium ions to balance out with the 1 oxide ion. We know water is H2O. The one thing that might cause a bit of difficulty here would be with the counting out the oxygen atoms. You have to acknowledge we've got oxygen atoms on 2 parts of the reactant side. Counting these out, we have 2 sodium ions really on the reactant side and 1 on the product side. How about oxygen? 1, 2 on the reactant side and 1 of them on the product side. And hydrogens, 2 on the reactant side and 1 on the product side. Actually, this is looking like it's not going to be too hard, is it? Because we've got 2 of everything on this side and 1 of everything on this side. I'm going to use one of those little like punctuation things. I don't know what they're called. To show what I'm doing to everything. Whatever number I put in there, I will be doing to everything because there's only 1 product, sodium hydroxide. So the whole thing is going to get multiplied by 2. And let's see what happens. Sodium oxide plus water reacts to make 2 NaOH. I think we can already tell this is going to be the correct answer, but it's a good habit of mind to verify your answers, using the same method you used as you're doing the question. We count our sodiums, oxygens, and hydrogens on the reactant side and on the product side. But we didn't do anything with the reactant side, so it's just 2, 2, and 2. No change. We didn't make a change. 2 sodium hydroxides. Well, let's be clear about this, by the way. A reminder. That coefficient, the number that comes before the formula, I'll say this again, applies to everything inside the formula. So it just doesn't mean just 2 sodiums. It applies to the oxygen as well. It means 2 oxygens. It applies to the hydrogen as well. It means 2 hydrogens. So now we, in fact, have 2, 2, and 2. The numbers all line up. They all agree with each other. The number of atoms for each element is the same on the reactant side as it is on the product side. That makes this a balanced chemical equation. So I hope that helped. I know this is it might seem like a bit of a dry subject, but it also becomes really important and useful when you are, for example, planning chemical reactions and planning, maybe you have a question about how much you might make of a given product if you have a given amount of the reactants. How much of a certain reactant you would need to make a certain amount of product. This gets into Chemistry 11 students, stoichiometry, and some of you Science 10 students are future Chem 11 students as well. A good experimental chemist is going to be a good cook. At least they'll understand, they'll appreciate the importance of the proper ratios of reactants to products. Balancing chemical equations is a key skill that you need to learn to do in order to succeed at that aspect of experimental chemistry. I hope that this has helped. I urge you to look at all of the resources that are out there, but these can be kind of a boost to you because these are, after all, problems on your question sheet, and I hope you found it useful.